A warm welcome to all. In today's video, we will discuss about an overview of corrosion. I am Dr. G. Kirtika from SRM Institute of Science and Technology, Chemical Engineering Department. In today's video, we will discuss about introduction to corrosion, mechanism of corrosion, and different types of corrosion. Corrosion control strategy will be taken up by the next series of video.
Let us understand the corrosion from its definition. So corrosion is defined as a destruction or deterioration of a metal or its alloy and the consequent loss of the metal caused due to the direct chemical action or electrochemical reaction with its environment. So basically it is a deterioration of the metal or an alloy where it leads to the loss of metal. So several metals undergo corrosion when it is exposed to air, water and the other substances. What could be the examples of corrosion if you can imagine? Rusting of automobiles, bridges, buildings, and also fogging of silverware and formation of green platina on copper. So all these we would have experienced in our day-to-day life where the material or the products in and around us are getting corroded and we also have a loss from it. So you can see here your unused vehicle which has been placed for a longer time used to get corroded, and if you are not paying any attention, the complete material will decay over a period of time. Similarly, you can see a tube which transports oil or pipe or which is being used in a chemical industry where the corrosion would have initiated from a smaller fitting and then it would have got progressed and it has led to the loss of material like or loss of the whole pipeline, which has to be immediately changed for proper functioning of the plant. So what is the universality of corrosion? So if we can understand the corrosion, corrosion is the environmental degradation which can happen not only in the metals or alloys, it happens in non-metals also like plastics, rubber, ceramics, whenever it is subjected to environmental degradation. Even in our human body, there is a corrosion, or we can say that it is because of the free radicals which is generated or oxidative stress which is leading to the degradation of our organs like heart or any other enzymes, pancreas, from which we get diseases such as cardiovascular disease and diabetes. So corrosion or degradation or loss of material happens in and around us. So now let us just understand what is the damage which is caused due to the corrosion. So the corrosion damage could be due to the discoloration or loss of appearance. You can see immediate corrosion damage which we can see is the loss of appearance or the disfiguration or the color change will happen and it lose to the loss of material. Sometimes we can we have to put a maintenance cost to save the material, or sometimes there is a loss in reliability and safety. Say if you are using such material, a pump or a pipeline in an industry, then there is a lot of uncertainty which helps in not which helps in predicting the law safety. Okay. Similarly, in extractive metallurgy in reverse or loss of precious metal, water, manpower, because whenever we are doing the extraction of the mineral from ore, so we have to input a lot of energy, water, power, right? So that is also being lost as a corrosion damage. So if it is too worse, if we are not paying any attention, then it leads to the plant shutdown, contamination of the products. Sometimes the corroded product, like the ferrous sulfate or the ferrous oxide or iron chloride, which gets into the stream of our material, and it also leads to contamination of the product. So there is numerous corrosion damage, which is basically starting from the loss of material, addition of maintenance cost to protect the material, and also there is a lot of concern with respect to safety and which ends up in plant shutdown. What could be the cost of corrosion? So if we can see in a plant, so in general, yes, whether it is a small plant or a larger plant or a multi-crore industries, the investment on the corrosion is huge. So they say that 3 to 5% of the total maintenance cost is goes for protecting or uh, safeguarding their material from corroding. So there can be a direct loss and also then indirect losses. So direct loss is because of the material cost, maintenance cost and design cost and also use of costly material to prevent or to avoid corrosion. So if we can take an indirect losses, it can be due to the plant shutdown, loss of production, and loss of valuable product due to the leakage and contamination of the product. So these are the indirect losses when compared to the direct losses of the material replacement. So again, if we can understand why do metals corrode? So as we say, right? So where do we get metal or a steel pipe from? It is basically from an ore. So ore which is present in the earth crust is taken, it is processed, it undergoes a numerous cleaning technique or what is separation technique, processing techniques before it gets into a steel pipe. So that's what it has been mentioned. It is an energy input process where we are inputting the energy to get a desired product such as steel pipe. Similarly, when we are using this pipe over a period of time, so this has an higher energy level, right? This pipe tends to come to a lower energy level, which is in the form of a rust. So the steel pipes gets corroded, it becomes a rust which has a lower energy. So whenever the material is at this lower energy level, it will be acting as a safe material and it will not get corroded. So ore will not get corroded. Ore is already in an oxide form, it is a stable form. Similarly, when it becomes rust also, nothing will happen to it, it will become a powder of iron oxide. But when it is in a steel pipe, it is exposed to atmosphere, it is at a higher energy level, an unstable energy level where it tends to corrode. So that's what if, it's been discussed, right? Any spontaneous reaction in the universe is associated with lowering the free energy of the system. So whenever the material tries to lower the free energy of the system, corrosion happens. So all metal except noble metal have free energy greater than their compounds. So noble metals are quite safe. So we cannot say that noble metal undergoes corrosion, but most of the metals except noble metals undergo corrosion. Now, apart from understanding the corrosion damage and the loss due to the corrosion, we come to the theories of corrosion. So, we can discuss two theories of corrosion. Mechanism of corrosion by hydrogen evolution. The other one is mechanism of corrosion by oxygen absorption. So let us just understand the mechanism of corrosion by hydrogen evolution. So here we can see from the diagram, when an iron tube, iron metal or a tube which is exposed to a acidic solution, an acidic environment, when a pH is less than 4, a small portion of the metal act as a cathode and the remaining portion of the metal will act as an anode and the corrosion is initiated. So you can see that at the cathode there is a hydrogen evolution. So the name is by hydrogen evolution, the corrosion happens. And in the anode there is a loss, right? Anode, the oxidation occurs. So corrosion occurs at the anode. Iron loses 2 electrons to become iron 2 plus ion. See, these 2 electron is taken up by the H plus. Where from H plus is coming? H plus is from the acidic environment. So from the acidic environment, H plus and 2 electrons from the ion system is taken for evolving hydrogen. So this type of mechanism is known as mechanism by hydrogen evolution. So that's what. So hydrogen evolution occurs at the cathode in a concentrated acidic environment. Usually ion surface with covered with an oxide at least at few points. So some portion act as a cathode with respect to other portion which behaves as an anode. So at anode we have an equation of iron getting iron 2 plus plus 2 electron, and at cathode there is an hydrogen evolution. So this hydrogen evolution type of corrosion occurs by displacement of hydrogen ions from the acidic solution. Next mechanism of corrosion is corrosion by oxygen absorption. So here the reverse phenomena happens. So here the pH of the system is in the alkaline atmosphere where any dust or any particles or any drop of water is placed on this, that portion alone lacks the access of oxygen, so it behaves as anode, and all the other portion is in the presence of oxygen, it behaves as a cathode. So cathode remains protected, same iron tube, but when we have a small drop of a salt solution like any solution or a small part of a dust, that portion, the portion under that metal will lack the oxygen. So that will initiate the corrosion known as oxygen absorption. So this will release 2 electron. These 2 electron is taken up by the oxygen which is present in the atmosphere. to form OH minus ion. So from this OH minus ion, again the corrosion is initiated for further processes. So again, if we can understand it, oxygen absorption mechanism of corrosion occurs in mildly acidic or alkaline environment when pH is greater than 4. Here, the process of rusting of iron takes place at an electrolyte of aqueous solution of sodium chloride. So you should have some Na plus ions. The area in which is not covered with the oxide will become anodic with respect to the other areas which become act as a cathode. So again, what will be the probable reaction at cathode and anode? At anode, there is a loss of electrons. Oxidation occurs. The corrosion occurs at anode. There is no doubt in that. So corrosion is initiated at the anode. So iron loses two electrons, and these two electrons and it forms iron chloride. These two electron is taken up by the oxygen because we have the other surfaces with good access of oxygen. These two electrons is taken by the oxygen to form 4OH minus. And since it is present in the acidic environment, you should be having Na plus, so which becomes NaOH. This also initiates a corrosion to form the rust in the further steps. Yeah, you can see both the anodic product iron chloride and the cathodic product NaOH are soluble in the water and it will dissolve with each other. Progress of corrosion. So we should also understand, apart from the mechanism of corrosion, whether it is by oxygen absorption or hydrogen evolution, we could only see a spot of the oxide on the surface of any metal. But this could be a very big corrosion which is happening at the iron metal piece. So as you can see, only a small portion is corroded on the top surface, which is fully covered or protected with a passive film. But deep inside, there is a process of corrosion happening where by the oxygen absorption mechanism, where there is more metal is corroded from the inside. So this is called progress of corrosion, where if you are not safeguarding or if you are not using any good corrosion protection strategy, this corrosion will be initiated and we could have only loss of material. As we can understand from the theories, we can also understand the electrochemical theory of corrosion. So if you have to have a corrosion, a large number of galvanic cells has to be formed with small anode and cathode regions. So oxidation always occurs at anode with the initiation of iron metal to Fe2 plus 2 electrons. So this Fe2 plus further forms iron oxide, and this iron oxide end up in forming rust, which is Fe2O3.3H2O. So this is the end form of corrosion, and this is the most stable form of the iron, which we have discussed in the previous slide. Now, next coming to the classification of corrosion. So we can classify corrosion in two forms. One is wet corrosion, the next one is dry corrosion. So wet corrosion, as the name says, the wet corrosion involves the reaction in an aqueous medium. So the conducting surface of the metal undergo electrochemical reaction in the presence of oxygen or moisture present in the atmosphere. Example, rusting of iron. So the both mechanism of corrosion is because of wet corrosion in the presence of aqueous medium. So most of our corrosion comes under the category of wet corrosion. Next, coming to dry corrosion. The dry corrosion is a rare phenomena. Example, there is no, as the name says, the dry corrosion should not involve any moisture. Due to the direct attack of metal by the dry gases, we can see this corrosion happening. Example, attack of gases with SO2, NOx to form corrosion. So we also have a series which has been listed in the literature called galvanic series, which segregates the metals and the alloy based on the order of the corrosion potentials in the environment. So as you can see, there is two ends. One is active end, the other one is passive end. So passive end are all noble metals, which is more stable, which is not prone to oxidation and corrosion. But active ends like magnesium, zinc, aluminium are all highly prone to corrosion, and we need a passivation phenomena to protect these materials, or to use these material in a real-time atmosphere. We should protect them from the corrosion and use it. So types of wet corrosion. So what are the different types of wet corrosion which we are going to discuss in this presentation is differential metal corrosion, differential aeration corrosion, waterline corrosion, pitting corrosion, and stress corrosion. So these are all the different types of corrosion which comes under the phenomena of wet corrosion. Differential metal corrosion. So as the name says, difference in the metal. So when we are putting two different metals together, the literature says that there is a phenomena or there is an initiation of corrosion between the anode and the cathode. Example, zinc as an anode and iron as a cathode, or iron metal as an anode and copper metal as a cathode. Similarly, iron metal as an anode and zinc metal as a cathode. So then we can see when two dissimilar metals are in contact with each other, the metal with a lower potential acts as an anode. Here, among the two metals, whichever has a lower potential, that will take the role of anode, and the higher potential will act as a cathode. So examples, you can see a difference in the bolt and the nut, different materials of the bolt and the nut, steel screw with copper sheets and steel screw with copper washers. Then differential aeration corrosion. So as we get the name, when two different part of the same metal is exposed to different oxygen concentration. So here we can see if we have a iron rod which is partially dipped in the water and the rest portion of the iron rod is being exposed to the atmosphere, then we have differential aeration corrosion. So less oxygen in the iron rod will behave as an anode, because whenever it is immersed in the water, it becomes the access of oxygen is less, so it acts as an anode, and the surface which is exposed to the atmosphere act as a cathode. So example, an iron rod partially dipped in water, a part of the nail which is in the wall undergo corrosion, and third part of the metal rod also undergoes corrosion. So you can see here, because the metal which is closer to the wheel is almost exposed to the water, like it travels in the rainy season, and also whenever it has a high moisture content exposure. So this portion is exposed to the corrosion rather than the other portion. So this acts as an anode and all the other portion act as a cathode. Next corrosion is water line corrosion. So here, as we can see, when a steel tank is partially immersed or partially filled with water for a longer time, the inner portion of the tank below the water line is exposed to less oxygen, and the outer portion has more oxygen. So as we see from a figure, a ship which is taken out from the sea, or most of the part of the ship is inside the sea. So it has less access of oxygen, so it behaves as anode, and the top portion has more oxygen and it is protected as cathode. So these type of corrosion is known as waterline corrosion. You can see here and the other picture also. So a distinct brown line is formed below the water line due to the deposition of rust. So ships which is partially immersed in a sea for a longer time undergo waterline corrosion. So next is pitting corrosion. So we would have seen some structures like this when we come across different metal structures, right? Where we just see a small dot and we predict that nothing much would have happened to the structures. But this is a type of a corrosion known as pitting corrosion, where a small dust particle get deposited on a steel surface, and the region below the dust particle act as a anode as it has very less oxygen, and the remaining surfaces will become cathode. So there is an initiation of mechanism of oxygen absorption type of corrosion, and hence it starts, the metal tends to corrode. So the formation of small anodic and large cathodic region results in intense corrosion below the dust particles. So this type of corrosion we have already discussed in the mechanism. So the same corrosion is being named as pitting corrosion on the surface of the steel structures. Next is stress corrosion. In stress corrosion, the portion of a metal under stress will act as an anode and the rest part of the structure will act as a cathode. So now here it forms a galvanic system, and hence anode part is small in area, that will tend to corrode, and the cathode part will remain unaffected. So it's highly specific in nature, and the examples we can have is caustic embrittlement, where it occurs preferably in the industrial boilers. So in industrial boilers, when we are using the raw water for steam production, that too at a high temperature and an alkaline environment, these type of stress corrosion tend to happen. So the untreated water, the raw water, has Na2CO3 and many other salts and deposit. So it will be hydrolyzed at a higher temperature to give NaOH. So this NaOH will act as a caustic. It will generate alkaline environment inside the boiler surfaces, and it flows into very hairline cracks and surfaces. Like it will penetrate into all these small cracks. From there, it tends to initiate the corrosion, because the steel tank, so the boiler steel tank has iron in it, and it attacks the sodium hydroxide, attacks the iron molecules, and it initiates a corrosion in the boiler. So the stress corrosion, a very good example of the stress corrosion, occurs in industrial boiler, which is known by the mechanism of caustic embrittlement.